Let's use this regression model to work on testing against a different constant. So let's suppose I wanted to take a look at this model where it says somebody's years of education is determined by some measure of ability from some standardized scores or something. The mother's education level, the father's education level, and number of siblings, which is expected to be negative because if you have too many siblings, you can't pay as much attention to working with one child. Higher ability, higher education, higher mother's education, higher father's education, higher education. So those positive and negative signs indicate what I expect the effect to be. So let's suppose I believe that right here we say the effect of mother's education that we have estimated is 0.173 approximately. So that means each additional year that the mother has for education is raising the years of education for the individual by 0.17. We can note right here that the very tiny p-value is indicating that it's highly significant, and all of the variables in our model have highly significant coefficients. So we already know it's significant. Let's suppose we want to find out if the effect of plus 1 year of mother's education is associated with greater than 0.10 in the individual's education. So we already know it matters, but what we're trying to figure out is some sort of testing of the magnitude of the coefficient. So what we would say then is we're testing with regard to beta 3 in the population. If we think it's bigger than 0.1, that goes in the alternative hypothesis, and no different than 0.1 would be the null hypothesis. Let's suppose I'm going to use a 5% level of significance. Now let's take a look at the t-test. The t-test will change because we're not testing as compared to 0 anymore. So our slope coefficient is 0.17336. Our standard error is 863. And now I'm testing against a hypothesis of 0.1, so I need to subtract 0.1. And in that case, my t-test will become 0.07336 over this standard error. Same standard error. And I will get 2.565 as a t-test for my different hypothesis test. My next step is to take a look at what happens to my critical value. I recommend drawing these to think about every piece of what's happening. So now this 0 on my t-distribution still represents the null of a 0.1, but we shifted it by subtracting the 0.1 off over here, so that 0.1 is represented by the middle of the distribution. I'm testing a greater than, which means I need my rejection region on the right-hand side, and it still needs to be 5%. if I look up T critical in R or in Excel, let's figure out what we would use for degrees of freedom. So degrees of freedom is n minus k, however many parameters we have. So we can look up here and see that we estimated 1, 2, 3, 4, 5 parameters. That was 5. And the problem gives us that this was the degrees of freedom. So what I know is that 1225 was n minus 5, which shows me that n actually was 1230. But when I'm looking up T critical, what I want is a T critical with degrees of freedom of 1225 or n minus 5 and a 5% tail. And if I look that up, this T critical is 1.646. So remember, that's the start of the rejection region. That's where I then determine where my t-test ended up. So my t-test was this 2.565. And if I were interested in using the p-value for this, I would need to find out the size of this tail to the right of 2.565. But it's nowhere on the table because the table doesn't know I'm comparing to a 0.1. But just using t-test and t-critical, I can see that since t-test is in the rejection region, we reject the null at 5% level of significance. And what this means is, yes, we have shown effect of the mother's education is greater than 0.1. Again, we've shown it at 5% level of significance, which means we've shown it, we believe in it, but we're acknowledging there's still a 5% chance that we have mistakenly rejected the null. But that's still, we're very, we have quite a strong result because we got quite a ways past that 5%. So this would be a strong result.